Okay, so that's the what you call the first part of the first, and the second type. Um, let's see. Okay, but before that, we call the um, uh, comparison test. Let's see what we call it comparison test. Okay. So if we have a functions which is positive, say at least not negative, um, right? For example, um, say for x, some a, and to the right of a, say, all right? Okay, so what we have is that uh, first thing, if this integral, the improper integral from a to infinity, g of x converges, then f of x also, this improper integral also converges. Okay, and second is that if this one diverges, then the bigger one so if in this case we just say that bigger than converges, sorry, smaller than converges means converges, okay, and bigger than diverges is diverges, okay. Typically, uh, more than converges is just then, okay. Okay, so let's all right, so let's say um, so check whether this integral from say it, which is okay. So let's see here. Uh, let f of x. So if this integral is, I would say this is nasty, okay, with x squared plus cosine. So we don't have a integration method to compute this type of integral. Okay? But we know some comparison that f of x, let's see this one. Okay, so we know this is non-negative, right? Because this is non-negative. So you put absolute value. Okay, and because we make this smaller, how you compare this to this one? This one is larger than x squared because we have additional cosine, absolute cosine. Right, so 1 over this is becomes larger. Okay, but we know that from so this is the case of smaller and converges. Then so the only thing is we don't know the exact value of that, but we know this converges. And if it converges, then you can use integration and just use computer to compute this one. Okay. Questions? All right, I give you one. I just mention just the integral here. This is improper integral, first type, because this is infinity. Okay, let's pretend this is just a. Okay, and then drag a to the left, far to the left, going to a negative infinity. And if it is from a to -1, we compute this integral. So you won't have this one. Okay. Compute this one. Okay. Compute this one, integral from a to -1. So if you compute that, use your, this is just substitutions. So it's 1/2 e to the minus x squared. Okay, so this, we get this one here. All right, so taking limit a going to negative infinity, this just plus infinity, this going to 0. Okay, so this negative. Okay, so this is converges. So this is example of one that does not converges because this doesn't have limit. Okay, so doesn't have limit. Doesn't have limit, so this is diverges. Okay, so this is the case of, um, let's see, let's do this one. Okay, and if both limit exists, then that should be So say just let's split at 0. So and let's see from 0 to B. Okay. And suppose we just use the uh, this comparison. Um, so this one, okay, because 1 over compared to this one, this is smaller than 1 over x squared. Okay, then okay, and we know that this is a convergent because this square power more than 1, so power 2. Converges, and this one also converges. Okay, so this limit exists. So then the conclusion is this. Okay, questions? All right, so let's do the second type. So improper integral of the second type. Uh, type 2. So this boundedness of the functions of integrand. Okay, so type 1 violates the boundedness of the interval. Type 2 violates the boundedness of the integrand. And this one is more subtle because you don't see from the problem. Type 1 easy in the sense that you can see directly from the problem. If the one of at least one of this the bound is infinity, negative infinity or positive infinity, then it is a type 1. Okay. Let's just do this one. Okay. So this is type 1. Oh, sorry, type 2. Why? Because 1 over x squared is unbounded on this interval. Okay. Unbounded. So you see that you cannot see this from the interval. You just have to observe the functions. Okay. So in that case, not example. Uh, this is type 2. And what this type 2 means. Let's pretend Pretend this is just like from say from A to 1. So A is between less than 1, but clearly positive. Okay. And pretending this, then you get something like what you get compute is 1 over, sorry, x a1. So 1 over a minus 1. Okay. All right. So what we do here is that let's pretend just a1, but let's uh, drag the a closer to 1 from the right. Oh, sorry, not from 1 to 1. Because what we're doing here is that a here is but drag this there. Okay. Okay, so this gives you 1 over a minus 1. Oh, but then this is a is small, then this is large. So divergent. Okay. All right. So type 2 is the integral of, so is of improper of type 2 if uh, we have this a to the right is plus or minus infinity, or okay, so this is type 2. So just like this one is type 2, right? So in that case, um, if this is the case, is plus or minus infinity, then the improper integral is like, say, c to b, which is proper. But then drag the c closer to a. Okay. And if this is the case, right? If infinity is here, then just pretend this is d, just drag d to b. Yeah, this integral is, pretend this is from a to b. Yeah. So this is a proper integral. But then drag d to the b from the left. So this kind of picture might be helpful for you in finding the definition. Okay, questions? All right, so then let's do this one here. Uh, do this one. Uh, Square root of 8. Okay. All right, so this means 0 and 1. The problem at 0, because 1 over x squared is infinity at 0. So then just drag a close to 0. Okay, so this is going to be a limit from the right. Okay, so let's compute this one. So power negative 1/2. So well, we can 1/2. So this is 2. 2 square root of x limit. Okay, so plug in 1. So this is 2 minus 2 square root of a limit. With this going to 0. So then this is 2. So this is purchase. Okay, from 1, we know that here, example 1, here, divergent. So this is right. In fact, let's see. Let's do this one. Uh, we don't need to compute this because let's see. For p, let's just do this one. Was 1, right? And this is 1. Okay. And if p is larger than 1, p larger than 1, this is p larger than 1 there. Okay. And p smaller than 1, uh, oh, right, 1 is the other way around. Smaller than 1. So let's see. 1 over x to p is smaller than 1 for x. Sorry, this is if p is larger than 1. P, sorry, this is larger than 1. Okay, so we know this one is 1 over x divergent, so this is divergent also. Forget this one here. Yeah, get this one first. Let's just leave it. 0, 8, 1, x, so equals, this is ln of x. Okay. So plugging 1, that's 0. Plugging a, this is ln of, sorry, a. Then something wrong with it. Okay, so this is the case of divergent. Okay, so power p larger than 1. This is the case of divergent by comparison. Okay. P, this one going to divergent if p bigger equal to 1, convergent p less than 1. Okay. So we can use uh, this comparison method is powerful actually. But you see, you should notice this one here. Or convergent is for p bigger than 1. Divergent is for p. But if you compute this type 2, this is type 1, this is type 2, the other way around happens. This one is divergent for p 1 and convergent for p there. Okay. All right, questions. Okay, let's do some example from the book. All right, so let's see. The one with the limit, okay. Where is that? This is the number one is type 1. This is type 1. All type 1. we're looking for type 2. Oh yeah, this one. Type 2. Oh, I should mention this type 2. See, where is that thing? Wrong. All right, here. This is something wrong. For example, if you don't recognize, you cannot recognize this as a improper integral, you forget to notice that the x0, this is unbounded. Okay, so just you proceed as if there's nothing happens here. So this, and you plug in the bounds -2 and 1, you get a number. Okay, but it didn't say anything actually, because this is wrong. Why? Because the this is divergent. Let's do this one. Where? And this is the wrong one. So you forget to identify the this is unbounded. Forget to identify 1 over x squared is unbounded at x equals 0 inside the. Okay, and if you forget to do this, just directly compute this one. The integral 1 over x, plug in -2 and 1. So you get 1 minus, plug in 2. This is plus f. But this is the wrong one, because it is improper. Because the integral is improper. Okay, how do you compute this one? Okay. Let's split this up to this one here. So this is still in questions. Let's split this up to from -1, -2 to 0. Right? And from 0 to 1. Okay, but now because oh, what's wrong with the problem is at 0. Okay, So we pretend this one, all right. So this is, say this is just B, and then push the B closest to zero from the left. Okay, so this is B, and here, instead of zero, this is A, but pushes zero from the right. There. So let's compute this one. The first one, uh, well, or the second one. The second one is, we know this is the divergent. If one of these is divergent, then the whole thing is divergent. Okay. This integral converges if both limit uh, in right hand side converging, but with this not. So this integral okay. Questions? The third type you have combinations. Is, for example, there. All right. We know there are two problems here. 0 and this infinity. Okay. So we split this up. Okay. So let's say A to B, drag A closer to 0, drag B closer to. So that's the idea. Okay, so we compute say from 0 to 1. Okay. This limit, not from 0 to 1. Say to A, drag A to close to 0. And from 1 to B. And drag B to infinity. The thing is, why 1 here? 1 is just convenient because that's easy. Okay. But with t integral, so 2 is larger than 1. T equals to larger than 1. Okay, so this is different. But this one, we know this is t equals 2. But this is the case of divergence because type this is type 1. This is type 2. Because one of the limit is divergent, then the whole thing is divergent. Yes. Yes. divergent, then the integral improper, sorry. Divergent. Okay. All right, so that's the combination of type 1 and type 2. Combination of type 1. Okay, questions? All right, if not, then we'll stop here. So the material for the joint quiz will be up to this point. So I'll share the notes and the video after this one. All right. And if there's no question, then I should stop the session, the record here.